Thank you very much. Today I'm going to talk about my recent works with my co-author Zaher Hani from the University of Michigan for the last like 5 years on the topic of Hilbert-6 problem in the setting of interacting waves. And of course, we'll start by describing the more classical setting of Hilbert-6 problem for particles. Okay, so the story goes back to the Hilbert's lecture on the 1900 ICM, where he introduced this list of 23 mathematical problems to be solved in the 20th century, and we are going to focus on the sixth problem that he raised, which had the description of mathematical treatment of axioms of physics. I think this is a title that he actually said in a lecture. Of course, this topic, if you just interpret in this way, is extremely broad, and actually, if you think anything in modern mathematical physics will be interpreted as a rigorous treatment of theory of physics. So actually, later on in his article in 1902, he actually specified two specific problems under this topic. And if you look at this, so the first specific question that he mentioned was actually the rigorous foundation of the theory of probability, which was unknown at that time, but of course it has now been completed due to all these works in 1930s, 40s, and so on. And another specific question that he mentioned in his article was connected to this derivation of the continuum mechanic, for example, the Euler and Navier-Stokes equation to the microscopic particle system. And he wrote that the problem of developing mathematically the limiting process, and the limiting process was referring to the earlier work of Boltzmann, in the study of kinetic theory, which lead to from an atomistic view to the laws of motion of a continuum. Okay, so this is actually the second question that Hilbert actually specifically mentioned in his paper, and actually, thanks to the research, the whole research of the 20th century, this problem has seen a lot of progress, but it still has not been completely solved. So, okay, so right now we'll focus on this problem in this more precise sense, mathematical foundation of the macroscopic limits of Boltzmann kinetic theory. So, roughly speaking, the starting point here, we're having this microscopic system of interacting particles. So we can have the classical kind of so-called half sphere dynamics, where the particles are just half spheres, where they encounter, they collide with each other in kind of elastic collisions. Or there can be particles with charge and particles that are interacting via some forces given by some potentials. So there are many different models here, but starting point is that we have a many particle system. And then, which happens, so this particle system happens at the microscopic level. And then we are going to take the limit, the so-called thermodynamic limit, where the number of particles goes to infinity, and the the size of individual particles goes to 0. And we arrive in a limit, the so-called Boltzmann equation that happens in the mesoscopic level. This is the second step in the process, and then we are going to take one further limit of the Boltzmann equation, essentially fluid equations. We are going to take this collision rate to go to infinity, and we are getting from the Boltzmann equation to this continuum fluid equation, for example, the Euler or Navier-Stokes equations. So this is the kind of three-level picture that can be viewed as two steps from the particle set picture to the Boltzmann picture, from Boltzmann picture to the fluid picture. So since our talk we focus on the first step, so we'll briefly review the second step in next slide. So you see we go from this picture, particle picture, to the Boltzmann picture by taking the kinetic limit and then taking the hydrodynamics limit to the fluid equation. I think this picture is taken from Wikipedia. So these two steps of progress that I just described. So I'll briefly say that the second limit is now kind of better understood. So there this work of Damasio, Esposito, and Leibowitz in 1989, which I think essentially established this derivation of fluid equations in the setting of strong classical solutions, and the work of Gauss and Saint-Raymond in 2004, which established this derivation kind of in the Leray-Hoff setting of solutions. Of course, I'm skipping a lot of literature because it's not the main thing I'm talking about. So the main difficulty here comes from the first step, going from the particle dynamics to the kinetic equation, and in this case, we're talking about the Boltzmann equation in the classical setting, and then this would be actually the wave kinetic equation in our theorem. Okay, so this is the setup of the problem. We have a start with the particle system. I want to derive the kinetic equation in the limit where the degree of freedom goes to infinity. Okay, so we have this is a more precise description of the settings. We have n particles, where n is something really large, and these particles themselves, they are small objects. So we will view them in classical problem. We view them as small kind of balls, spheres. Okay, so n is going to infinity, and this size epsilon of these particles is going to 0 in the limit. So we have in this picture a huge number of particles interacting with each other, and of course the interaction is given by different models, and here we're considering essentially the simplest model of the hard sphere collision dynamics, which I'm going to define in the next slide. So the question is, can we describe the motion of the system statistically in the limit when n goes to infinity? So because the idea of statistical physics is that which starts from the work of Boltzmann, is that it's really hard to describe the individual motion of each individual particles because there are so many of them. But what we really care about is the statistical properties, like the density of the particle, like how many, if you divide the region into two, then what portion of particles will belong to the first region, and what portion of particles will belong to the second region. And this is described by the density function of the distribution of these particles. And that's a thing we're interested in. Again, here is all about the classical setting of particles. Later on, when we go from particles to waves, there will be everything here will have the wave analog in the waves. Okay, so this is the hard sphere dynamics. So basically, you think each particle is a hard sphere occupying kind of diameter epsilon region in space. So if the distance between their center is bigger, then there is no collisions, and these just travel kind of by straight lines. And if there is the distance become epsilon, which means there is a collision, and then their velocity is going to change. So basically, if you have imagine you have two particles, colliding with each other, and then they are going to move along to new velocities, and the velocity is given, the rule is given by this elastic collision formula. Essentially, it's like the velocity that is parallel to the connection of their center is at a change, and the velocity that is orthogonal to this center connection stays the same. Okay, so we have this rule, and then this is pretty simple if we only have two particles, but then now we're having very many particles, and any two of them may collide, and you see that their velocity are changing with every collision, and then you see after a few collisions, these dependence will get to a mess, and then the question is, how do we describe the statistics of distribution of these velocities, at a later time if we start from time 0. So one feature of this collision system is that it is a time reversible system and is a volume preserving dynamical system. However, we'll see in the limit that the Boltzmann equation we derive is time irreversible, and there is actually a deep reason for that. We may get to this if we have time. Okay, so this is this half-sphere system, and then next slide we look at the object we're interested in, and these are the density functions. Remember, this means the probability density of that a particle is found in a particular region of space and particular region of velocity, and this is defined by the so-called one particle density. And then you can have multiple particle densities, two particle densities, which means that the probability that the two particles can be found at this position and this velocity. Okay, so this is the object we're looking at, and assume initially that these particles are random and independent. So, for example, there are multi-point density functions is a factorization, is tensor product of the one-point density functions. Okay, so this is the setup of the problem, and then assume we're assuming this sort of Boltzmann grad scaling limit, which is the classical thing in starting with Boltzmann. I mean, of course, you can consider different scaling laws, but this relation basically means that Boltzmann grad, so n epsilon squared equals 1. The reason of this is that, so here n is a number of particles and epsilon is the size of particle. So basically, if you think you have one particle that goes in a straight line, at time 1, and the size here is epsilon, then basically the volume of this particle is covering is exactly epsilon to the square in 3 dimensions. So essentially, you can think that the probability that another particle collides with this particular particle x is like n times epsilon squared, which is about 1, and this is so-called collision rate. Essentially, this Boltzmann grad limit is saying that the collision rate is a constant rate, in unit time, and that's why we are choosing this, because we want to derive our Boltzmann equation, the kind of the increment or kind of the perturbation to density function at unit time. Okay, so then we're doing this, assuming this relation, and we're taking the dynamic, the kinetic limit n goes to infinity, and we are interested in the distribution of the particles and the density function at some later time. Okay, so here comes one key prediction starting from Boltzmann theory, is that these independent. So remember that initially these position and velocity of the initial particles are independent. Now this independence is certainly not preserved due to all these collisions. This is because it's a pretty nonlinear thing. However, the expectation is that these independence should be in the limit. So in the sense that these dependence caused by collisions, in the end, they will not. They will be kind of a vanishing term when you take the limit when n goes to infinity. And this is referred to as the propagation of chaos in the physics literature. That these independence is restored, and in the limit, joint density function is still factorized as a tensor product of individual density functions. Okay, and for now, let's say we believe it. Then the multiple point density function is going to be the tensor product of a single particle, a one-point density function. Now, one-point density functions depends on time, depends on the position x, depends on velocity v. And exactly this thing is going to evolve in time, according to the Boltzmann equation. And this Boltzmann equation is written here. So it's a transport equation, dt plus v dot grad x f equals the right-hand side. So here the right-hand side will be 0 if there was no collisions. But now, since we have a collision, we have this collision kernel called QF, which is given by this integral. So this is not the traditional way of writing it, but it's equivalent to the traditional way in 3 dimensions. I'm writing this in this way because I'm going to compare it with the wave kinetic equation setting later on. So it's you see it's these two delta functions imply that they are, the integral is supported in the region where v plus v2 equals v1 plus v3, which corresponds to the conservation of momentum after this collision. So basically here you write this is v, this is, okay, so this is v1, let's say v3, this is v, this is v2. And then this delta function corresponds to the conservation of energy, that the v1 squared plus v3 squared equals v squared plus v2 squared. Okay, so this is the Boltzmann equation, and of course there is plenty of literature concerning the solution theory to it and properties, which I'm not going to talk about because that's not the focus of this research. Okay, so now the problem is clear. We start from some independent dynamics, independent initial state, and then we go through these collision dynamics, and we want to justify the propagation of chaos, and then the evolution by the Boltzmann equation. And so here, the first mathematical result in this direction was by Lanford in 1975, which essentially provided justification of these, of everything, these derivation of Boltzmann and propagation of chaos for sufficiently small time, t much less than 1. So the reason for sufficiently small time is that we need to perform essentially a Taylor expansion, and in order for this Taylor expansion to converge, we need to restrict to a sufficiently small time for a power series. Okay, and then there are other results which I'm skipping. I cannot list all the literature. For example, there is work in the 90s concerning the small data problem. And the next major kind of milestone in this direction was the work of Gallagher, St. and Texier in the book of 2014, where they actually fixed some kind of ambiguity in the original proof of Lanford, and they also obtained kind of explicit convergence rates of these dynamics, again, for sufficiently small time. Okay, and more recently, there has been a lot of progress, like in this direction, due to the work of collaboration of many people, Bordino, Gallagher, St. Raymond, Salmonella, and I think other people, starting from 2016 to very recent, where they were studying the kind of the fluctuations around the Boltzmann equation. So basically, you can see they view this Lanford theorem as a kind of a law of large numbers, and then the kind of the perturbation around that would correspond to the central limit theorem, where they basically derived that these fluctuations satisfy the linearized stochastic Boltzmann equations. Again, these are for short time, and only at exact equilibrium were they able to obtain a result for long time. Okay, so this is a very brief introduction of the mathematical works in the particle setting, because our main thing today is a wave setting. But before that, of course, all these things we described have led to one open problem of how can we, is it possible to derive the Boltzmann equation from hot sphere or any other dynamics for arbitrary long time, not restricted to the local in time solutions, of course, as long as the solution to the Boltzmann equation exists. So we know, for example, the solution to the Boltzmann equation exists if we have small perturbations to the Maxwellian, and in this case, do we get this derivation for arbitrary long time? So this is perhaps one of the most important open questions in the field, which we may get back in the last slide. But for now, let us briefly finish the introductory discussion in the particle setting, and next let's move to the wave, in which I'll talk about concerning our recent works. So before that, is there any questions? Okay, so then we can move on to Hilbert 6 problem for waves. And so you see, like in the time Hilbert delivered his lecture, there was still very few things talking about relating concerning the quantum physics. But we know that there were lots of developments of the quantum physics in the 20th century, and especially is this famous idea of wave-particle duality. And so since we we have been considering the Boltzmann kinetic theory of systems of particles, and the natural thing is that we also consider corresponding kinetic theory of statistical physics for the system of interacting waves, and this leads to the subject of wave kinetic theory. And again, the fundamental question of the Hilbert 6 problem has also been asked in the wave settings, in the setting of quantum physics, and many of these questions are still open. So let me mention the first occurrence of the wave kinetic theory, where the role of Boltzmann equations is replaced by the wave kinetic equations. So actually there is a wave kinetic equation which contains cubic terms compared to a Boltzmann equation which contains quadratic terms, and there is something else called the quantum Boltzmann equation or Boltzmann-Nordheim equation, which contains both quadratic and cubic terms, and they are concerning different settings. So starting in 1920s, 1929 paper of Paris, who wrote down the first wave equation for anharmonic oscillators. And then, so there is this work of Nordheim and Uhlenbeck in the 1920s, 30s, where they introduced this quantum Boltzmann equation, where they were considering quantum particles, bosons and fermions, instead of classical particles in the Boltzmann case. And then there is this work of Hasselmann in the 1960s, who applied the wave kinetic theory to water waves, and this has led to a major kind of subject in applied mathematics, where they apply this wave kinetic theory to ocean forecasting. They are actually solving these equations to make predictions about ocean surfaces. And also I mentioned the work of Zakharov, again in the 1960s, who actually did a lot of foundational work to the wave kinetic theory. And one thing he did was he discovered this energy cascade phenomena, which is governed by something which is now called the Kolmogorov-Zakharov spectrum. This has pretty much similarity with Kolmogorov spectra in hydrodynamic turbulence, and because of this reason, this theory of wave kinetic theory now also has the name of wave turbulence. Okay, so again, these are some brief remarks in terms of physical literature, and now it has been applied also in the oceanography, in the plasma theory, in the theory of optical fibers, and all other kind of things, which will not get into details because they were mostly concerning the applications of the wave kinetic equation, especially the energy cascade and all sorts of other things. On the other hand, what we'll do today is to establish the foundation of this theory, which is a derivation of the wave kinetic equation. Okay, so we'll see the wave equation in the next 1 or 2 slides, and before that, we'll go over the setup. We'll see this is pretty similar to the particle picture. So here we have particles that are replaced by the Fourier modes. So that's in the so-called homogeneous setting, where there is no fluctuation in space. And you can also consider so-called inhomogeneous setting, where the strength of the field is different at different place of space, where you introduce a kind of extra transport term to this equation. But for simplicity, let's look at the homogeneous cases, where these particles are represented by Fourier modes. In the inhomogeneous case, they will be wave packets. And then in the large periodic box of size L, this is so-called the large box limit. So the picture here is at the large box L, and if you think of the Fourier modes, and if you think of Fourier modes at frequency 1 unit frequency, they are going to have so this is frequency 1, so this is t, let's say this is t hat. Okay, so this distance here is 1 over L. And then if the dimension is d, then this number of Fourier modes, which is the degree of freedom we're looking at, is L to the d. In 3 dimensions, that's L to 3. Okay? So there is a subtle difference between this picture and the particle picture, is that is that this is like L to 3 instead of L to 2, which is what happens in the Boltzmann case, which makes it slightly different in quality, but in any case, it's still the same kind of kinetic limit where the degree of freedom goes to infinity. Okay, and then so these are the particles, these are the objects, and then the collisions or interaction between the particles are replaced by the nonlinear interaction of waves. And in general, it can be modeled by any nonlinear dispersive equation, just like you can model the interactions of different particles by direct collision or kind of any potential, anything else. So you can model this by any nonlinear dispersive equations. And there is a parameter alpha indicating the strength of the interaction. And this alpha will go to 0 in the so-called weak nonlinearity or weak interaction limit, corresponding to the size of the particles going to 0 in the Boltzmann setting. Okay, and the choice of nonlinear dispersive equation is pretty much arbitrary, but we shall consider the canonical case, which is the cubic Schrödinger equation. This is, in some sense, the canonical nonlinear dispersive equation, and it's also pretty much the simplest nonlinear dispersive equation you can think of, and it's something that occurs in a lot of different physical models. So start with this. So L is the size of the box, represents the degree of freedom, and alpha is the strength of interaction. And then in the kinetic limit, we're taking alpha go to 0 and L going to infinity. And actually, there is a scaling law between them, indicated by some value of gamma. So there's a reason why gamma has to be in 0, 1, but I don't have time to explain. And again, we're dealing with homogeneous cases, which we'll see a distribution of U doesn't depend on the point of X in space. Okay, so this is the cubic nonlinear Schrödinger equation. And then the initial data, again, like in the particle case, we're having the states of the different modes. So in here, the objects are different Fourier modes, and the states of different initial modes, they are independent. So these modes are kind of the Fourier modes, and these U hat are Fourier coefficients. So here we have, ignore this, is normalization constant. So this here, the Fourier coefficients are given by some fixed function. So this will be the initial kind of profile. And then times is either K or IID random variable. So let's say they are normalized Gaussians. They don't need to be Gaussians, but just for simplicity. So these are IID random variables, and they are the point is that these are independent. So different the initial state of different Fourier modes are independent, corresponding to the fact that the different in the Boltzmann picture, the initial density is a factorizing. Here, if you write down the initial density function, it's also factorizing. Okay, so this is the initial data. And then the role of the one particle and R particle densities in the Boltzmann case are placed by 2-point and 2R point correlations. So the reason that we go from 1 to 2 is because in the Boltzmann case, the density is positive, but here, this U hat K, they are not positive. They are complex Gaussians, but if you look at their correlation, the expected value of U hat dot U hat bar, this thing is positive. So 1 point corresponds to 2 points, and R particle corresponds to 2 R points. Okay. So this is the exact analogy that we draw between the particle and the wave dynamics. And again, what we're expecting is that we're expecting the non-trivial things to happen at the so-called kinetic time. And what does it mean by this kinetic time? Again, it means the first time when a non-trivial interaction happens. So remember, in the particle picture, this is the time where this particle X is expected to have one collision with some other particle Y. On the other hand, this T kinetic is there. So this alpha minus 2 is the time of a single mode to interact with another mode. Okay, so this is you can think that this is the first time where non-trivial perturbation happens to the linear Schrödinger dynamics, which is given, you see, by this inverse power of this this alpha of strengths of the nonlinearity. Okay. When that's interested in the behavior of the solution and the statistical properties of behavior of solution at its kinetic time, tau times c kinetic for constant times tau. Okay, so as in partial setting, we expect this propagational chaos. The independence for Fourier coefficients, independence for modes is preserved in the limit. In other words, for any fixed tau, these random variables at rescale time tau is going to be asymptotically independent in the limit. And once we accept that, the only thing we need to solve for the full statistics is the one partial statistics, or kind of the 2-point correlations, which is this one. So it's an expected value of the square. So this second moment, you can look at higher order moments. They are corresponding theories, which I'm not going to talk about. And they will satisfy the Wave-King equation. And you see this Wave-King equation is exactly similar to the Boltzmann equation, except that you have a cubic nonlinearity instead of quadratic nonlinearity. The integral domain is exactly the same, except you have this cubic, you have this n1, n3 times n plus n2 minus n2 times n1 plus n3. And this cubic has to do with the fact that you have a cubic Schrodinger equation with a cubic interaction of the waves. Okay, so this is the Wave-King equation, and a few remarks. So we are in the homogeneous setting, so there is no transport term. If we add a transport term, which would be the d tau plus k dot grad x of n equals c of n, and that will be the exact analog of the Boltzmann equation, and the derivation is not too much different formally. I mean, if you can derive the homogeneous ones, it's not too difficult formally, conceptually, to get to the inhomogeneous one. There's some technical points, though. So the collision integral here is cubic, but with the same domain integration. And this is specific for Schrodinger, because for other dispersion relation, you're going to have a delta functions in other other dispersion relation here. Okay, so we remark that for the collision kernel for the quantum Boltzmann equation, it's just a linear combination of the quadratic and cubic ones that you see in the Boltzmann and in the Wave-King equation. Okay. So some earlier mathematical works. Again, I'm skipping a lot of literature. I'm only listing the major milestone ones. So earlier work concerned linear models, linear Schrodinger equations where the randomness comes from the random potential. The 77 work of Spohn, 2000 of Erdős and Yau, and 2008 of Erdős, Semhofer and Yau, where they essentially push this to the limit, even going beyond the kinetic time. And then the first work concerning the nonlinear problem was this work of this paper of Lucarini and Spohn, nonlinear but at equilibrium. And then the starting point of this recent research was Buckmaster, Zaher Hani, and Shatar in 2019. They started this work on nonlinear off equilibrium problems, but they were getting to a time scale which is much less than the predicted T kinetic. And then we know there has been a sequence of works in improving this on and on. So with my paper with Hani, and at the same time the paper of Colin Germain, we're able to get to this T kinetic to the 1 minus epsilon for arbitrarily a small epsilon. Okay, and so this is a good time to introduce our first main result, which establishes this validity at the kinetic time scale, alpha minus 2, for a short rescale time. So remember, this tau is a rescale time. Here we're assuming in our first theorem, this tau is assumed to be sufficiently small. So arbitrary scaling law, so T kinetic. Then in the limit we have this prediction. I mean, actually we are proving also propagational chaos and all kinds of other things, but I'm only listing here. For sufficiently small rescaled kinetic time. So this is this after kinetic time, after a small multiple of kinetic time, will end the solution to the Wave-King equation. Okay, so this is our first main theorem, which consists of 3 papers. The first paper in April 2021 will establish this derivation Wave-King equation, which is this limit, for a specific range of scaling laws gamma. And later on, we extended these to include the propagation chaos of these multiple point correlations, again, for the same range of scaling laws. And finally, we're able to extend the full result to general self-scaling laws. So actually, there was some interesting new phenomena that occurs, which I may have little time to talk about. And this, of course, matches state of art in a particle setting, which is this short time result of Lanford. Of course, the question is whether we can get to the fluctuation, which is something we are looking at, which we believe should be positive. And in terms of derivation, that's what happens. Okay. Before we get to our second result, so we have a few minutes. Before we get to the second result, let's discuss a little bit kind of what is involved in the proof of this short time result, in a wave setting compared to the particle settings. So main point in both proofs rely on these so-called Feynman diagram expansions. I mean, in the Boltzmann case, it's referred to the BBGKY hierarchy. In the wave case, we are dealing with these ternary tree expansions. In the Boltzmann case, it's binary tree because it's a quadratic equation. And here we have a ternary trees. I mean, we are not relying on a particular hierarchy, but we do have these kind of expansions, and then we're summing over all the expansions. So there is one difference actually in both cases is that in the wave case requires kind of an extra step which has to do with the pairings. So remember that in the particle case, we're having this n of, let me call it n of t, x, and v. So this thing itself is positive. On the other hand, in the wave case, we are having this expected value of u hat tk square, and this is the main thing that we have that is positive. On the other hand, what we expand is this u hat. So we expand u hat tk equals dot dot dot, sum of dot dot dot, and then we're having this u hat tk bar equals the sum of the conjugates, and then we're taking the product of those, and then that means we're taking the pairings between this. This is one crucial difference between the wave setting and the particle setting is that here we're having different, this one extra structure. So this is a structure we find in our paper, which we call couples, where you see we have two binary trees, and then the leaves of the binary trees are paired with each other, and these pairings exactly correspond to the pairings between these kind of Gaussian, multilinear Gaussian correlations. Okay, so this basically adds a kind of one further level of complexity to this problem, and there is a lot of technical difficulties. For example, the number of pairings grows factorially instead of exponentially, and these are actually something that we'll deal with in the proof. And second thing, I can only very briefly mention it, is that there are very interesting cancellations actually happening in the wave picture that is not quite seen in the particle picture. They're actually diagrams. So you see, this is a couple. I mean, it's a part of a couple. There are these pairings which are indicated by the same colors. So there are these couples on the left, and there is a couple on the right, and they actually exhibit very precise cancellation with each other. That if you don't have this cancellation, then your expansion will actually diverge, due to these bad powers. But these two things, they somehow exactly match each other. And this top picture is what happens in a certain range of scaling laws, and in the further range of scaling laws, you're seeing more complicated picture like the one in the bottom, and it's pretty much crazy. Like, why do you expect these two things? You don't need to understand it, but you just look at these two pictures. They are not at all isomorphic, but somehow there is a miraculous thing that happens between them. That there is a very subtle cancellation between these two pictures, and there are similar pictures of this form that actually allows us to extend the theory. So I've been giving this talk in different places, and people have been asking me, like, what is the physical intuition behind this? I don't know. I can only say it's a miracle, kind of a miracle and magic that these things happen. So, okay, so the second main point involved in this theorem. And okay, so now this is the final, we get to present this very recent work, which was done last year, where we actually were able to extend this main theorem. Like, remember, this main theorem was concerning the derivation of wave equation, for sufficiently small constant times tau, rescale kinetic time, and now we are able to obtain these for the first time this same result derivation of wave equation, but for arbitrarily long time. So here, arbitrary long time means as long as the solution to the wave equation exists. So of course, if the solution to the wave equation does not exist, then there is no reason to talk about the approximation. So this theorem established the optimal thing that as long as the solution to the wave equation exists, we are going to have this validity of this approximation. Again, up to the full lifespan of the solution. So with our, as far as we know, this is the first long-time result that is ever obtaining any kind of nonlinear kinetic limits in the context of waves. Okay, so we have a few minutes. So maybe I'll just explain it in words, like what's the key point here? The key point to obtain this long time, remember that why was the previous short time result restricted to short time, is because you need to perform local in time Taylor expansion that has to converge. But if you get to long time, this thing will not converge. So the idea to get to longer time is that we perform induction in time, and then we are going to divide your time interval into, okay, so 0, so this is 0, this is tau, and then we get to this delta, and get this 2 delta, and this 3 delta, and so on. And then we're going to go from each time interval to the next time interval. Okay, so the thing here is that if we go from each time interval to the next time interval, at time 0 we're going to have exact independence, but at time delta will not have independence. So remember, at this time we have independence, but here we have no independence. But what do we, the key problem is to identify what do we get for the statistics at this particular time delta. So there is no independence, but what can we say? They are not independent in the sense that they are having non-zero cumulants, and then we're going to have a precise description of these cumulants. So description of cumulants. And this description has to be very precise, that it has to respect the arrow of time, that you're only going forward in time and not going backward in time. And then there is this arrow of time, and because of this particular cumulant, it has to memorize all the interaction history of the full equation up to this time. So up to this time. And then at 2 delta, you're going to memorize the full interaction history up to this time, and so on. Okay, so this is a very, written down is extremely long, so I can only summarize it in one slide. Okay, and then this leads to new structures, which are called canonical, layered, couples, and gardens, and a lot of commentaries. So let me say that the main ingredients of this proof, there is a big part, there are a lot of analytic ingredients, but the main ingredient will be actually a commentatorial in this proof to analyze the structure of these couples and gardens that we talk. So there is one thing for the flow chart of scheme of proof, which I'll skip it. And okay, so last slide. So we are currently looking at the corresponding result, corresponding problem for particle systems, in the derivation of Boltzmann. So working on this with Hani and Ma Xiao, who is currently postdoc at Michigan, and we believe that using these techniques, we're able to get some kind of partial progress, at least on the problem. Okay. So let me finish by the next slide. So some further open questions. The derivation of the quantum Boltzmann equation, which there has been some recent results, but what is actually happening is still unclear. Connecting the kinetic hydrodynamic limits and going beyond kinetic time, and the turbulence cascade, especially how do you see the Zaher spectrum, is again a big problem, and the formation of the delta singularities concerning, how to, can you say anything, beyond the time where the wave equation blow up and so on. So many different, things that still remain unknown. Thank you.
Is there any question from the audience? Maybe I can ask a question. So for your, for the project you are working on, it's a hard sphere case or soft?
It has sphere case.
Hard sphere case.
Yeah.
And by the way, the actual long-time tau state, tau star, is there any relationship between tau star and air?
Okay, yeah. So first of all, if the blow-up time is finite, then tau star is up to this blow-up time. And then if the solution is global, then tau star, we can choose it to be something like log of L. And the best we can hope is might be log L, but this is unknown. I mean, like, if you want to get to like L to the power, this is very hard at this point. But we can get to log for now.
Okay, and this is also for gamma less than 1?
Any gamma.
Is there any particular reason why gamma cannot be equal to 1?
Yeah, if gamma equals 1, you need to assume kind of irrationality, because there is number theory problem which concerns, distinguishing the resonances and quasi-resonances. So basically, when gamma is bigger than 1, for example, these exact resonances will dominate, and then you get a different equation. So like when gamma less than 1 is still the quasi-resonance that give you the Wilkin equation.
If there's no more question, let's thank Yu again.